If you are familiar with playing natural harmonics, then you would know that natural harmonics can only be created and heard at specific points on the string of the guitar. For example, the 12th fret, the 7th fret, and the 5th fret. With this comes the fact that plucking and holding down at the wrong string will not create a harmonic. In fact, it only kills the vibration, muting the sound and making it unable to, make noise. I'll give you an example of this. This is the 13th fret. Again, this is the A string, and I'm plucking. We can do this again at the 11th fret and the 10th fret. You can hear somewhat of a noise, but the string doesn't really vibrate. What you're hearing is more of just the muffledness of the vibration. One basic thing to understand about the physics of guitar is the fact that the strings are fixed at both ends. As you can see, they're held down here and tightened by these nuts, and held down here, tightened again. So they are both fixed ends. This also means that they can vibrate in a multitude of different modes, which I'll show next. These different vibrational modes are considered harmonics. One harmonic is called the fundamental. It is the more dominant frequency, which determines which note that we hear. It is the most strongest and most influential of all the harmonics. An example of the fundamental would be an open string. So let's say the open E, that was pretty loud, the open A, open D, G, A, and E again. This is because fingers are not being held down, or nothing is being held down onto any of the frets of the guitar. Therefore, it is nothing but a natural vibration, and I'll show you what that looks like one more time. The strings of a guitar do not only vibrate in fundamental or an open note, but rather they're able to vibrate in many different vibrational modes, or harmonics, and they have decreasing influence as the harmonic number, or N, we'll call that, as that increases. The ideal string of the guitar would be able to vibrate in many different functioning patterns, which are harmonics. Each mode would relate to a frequency, which all combine to create the final product, aka the tonality, or the note that we would hear from the string. If I was to place my finger on the 12th fret again and pluck, it sounds like this. The 12th fret is the middle of the strings at each part of their fixed ends. Placing my finger there introduces what's called an additional node point on the wave. This prevents the string from vibrating at the point of contact, which then reduces the number of harmonics that are available for the string to vibrate at. This eliminates any harmonic patterns for the string to vibrate at without a node point at the center, again because we are pressing down at the center of the string. And those patterns are illustrated here. That would then eradicate the fundamental, which is the open string, which then leaves the second harmonic as the most influential, being the this at the 12th fret. That would be the second harmonic. That then explains why the 12th fret harmonic is an octave above the open string, even though the entire string is still vibrating. The frequency of n equals 2 is twice the fundamental, which then results in the pitch being an octave higher than the original fundamental vibration mode. The frequency of n equals 2 doubles the fundamental, and by doubling the fundamental, we bring up the note by an octave, thus explaining why this pitch on the 12th fret sounds higher than the original. When playing a natural harmonic, the reduction of the harmonic frequencies compared to the open string results in a pure tone, which is also just an open string, giving us the original note. If we were to think about a string and assume that its open frequency is, let's say, 110 hertz. So we're assuming that that open string is 110 hertz. Then that would mean at the 12th fret, since it's the middle, n would equal 2. So this would mean that the note would result in 220 hertz. If we were to go to the 7th fret right here, this would be a third of the entire string, which means that n would equal 3. This would result in a tone with 330 hertz. And if we were to do the same thing at the 5th fret, right here, well then this would be a fourth of the entire string. So n would equal 4, which would then result in the second octave, which would have a tone at 440 hertz. Now this is an incredibly musical arrangement of frequencies created simply by preventing the string or allowing the string to vibrate at specific integer divisions along the string of the guitar. So on specific lengths of the string that are divided equally, this creates the ability or lack thereof to vibrate and then create higher octaves or similar notes. Now, getting back to why natural harmonics can only be played and occur at specific locations of the string's length, let's imagine that a string can only vibrate in the following modes. Now I'll show a picture of that right now. Now, placing a node point at any of these, I'll show a picture, locations on the string or wave will result in a natural harmonic, as it is at least one vibrational frequency with a matching node point at the center. However, if we introduce points here, I'll show a picture, we can see that none of the vibrational modes have a matching node point, meaning this, so then this means that a string cannot vibrate at these frequencies of, any of these frequencies, and cannot then create a sound. So an example of that, again, would just be at the 13th fret, if I tried to pluck, 11th fret, 10th fret, but again, if I played the 12th fret, we still get a noise. Now, this isn't the only way to invoke harmonics onto a string of, any string instrument. Artificial harmonics are harmonics performed at a fretted note. Pitched harmonics are generated by thumb touching the string immediately after picking said string. Tapped harmonics are introduced node points by pulsively tapping the string, so like this. And with all of these versions of harmonics, the same physics applies. A node point is introduced on the integer division of the string length, which then generates a higher pitch note in comparison to the original note. This comprises of higher order harmonics lacking the fundamental frequency.